Hello folks, today we're going to be teaching you the 80s in your unit pack, which are significant figure notes. We're also going to be using the cover of your unit pack, so if you need to pause this, go ahead and get out your 80s and get out the front cover of your unit pack at this point in time. The notes, the rules I should say that we're going to cover are on the back of that front cover, and they will come in handy as we're going along. So I'm just going to kind of read you a few things as we're going along on the 80s. Again, pause it whenever you need to. First of all, it says no experimentally obtained value is exact because all measurements are subject to errors. That's why significant figures are significant to chemistry problems. So we have two terms. We have accuracy and precision that we're going to talk about here. So accuracy, and I would probably underline this because you'll see this on your first quiz. Accuracy is how close to the true or accepted value you actually came with your data. So an example is a boiling point of water is known to be 100.0 degrees Celsius, and a student measures that boiling point at 99.9 degrees Celsius. That student is very close to the true or accepted value, so they did it with a great deal of accuracy. Going next, we have the word precision. Precision is the degree of exactness of a measurement, or how reproducible a measurement is. And if you can reproduce a piece of data over and over and over again, you have a very exact piece of data. So we have three students, and they measure the room with a meter stick. And Alfonso measures the room, and it finds it's 10.94 meters. And Betty measures the room and finds it to be 10.93 meters. And Kathy measures the room, and it's 10.93 meters. All these three measurements are very close to each other, so we can say we have a good degree of precision because the data is very reproducible. We can look at another example right here, a little bit more gruesome, but at the shooting range, Marge pumps 5 shots into a foam black bear, and all 5 shots hit the hind foot, the back foot. Her scope must have been sighted in wrong since she was aiming for the kill zone, or the center of a target. Her shots were inaccurate, however, they were precise since they all hit the same spot. So her data, per se, would be very reproducible because she kept hitting the same spot. Again, reading to you, it says, if a measurement is reported with either too many or too few digits, it is not possible to tell how precise the measurement really is. A calculator exaggerates the precision of a calculation by reporting too many digits. Significant figures are used to indicate precision. Significant figures are digits in a measurement that have been measured, or certain digits that we are very certain of, plus 1 digit past the smallest marking, which is the estimated digit. So the more precise an instrument is, the more numbers you're going to have and the more accurate your calculation. So now we're at the bottom of your sheet, and we're going to count the digits, and we're going to start to get used to the rules. Now these rules are also found on the cover of your unit pack, so if you do not have that heavy-duty piece of paper from the front of your unit pack out, pause this video and get it. So in this particular rule, we look at this and we have 2 digits, 2 significant digits, and we have 3 significant digits, and we have 4 significant digits. And this rule is pretty simple. All digits, with the exception of 0, are considered significant. So this is the very first rule on the back cover of your unit pack. Now we're going to the second rule, and we call this trapped zeros. So any zeros that are trapped between other numbers are considered significant. So here we would have 3 digits, and here we would have 4 digits, and here we would have 5 digits. All because those digits are trapped between other numbers. And that is rule number 2. Now, rule number 3 is where we start to get a little bit more of a variation of answers that people will come up with. So there's a little bit more difficulty level with these questions. I look at this right here, and let's say I put this on a balance, and instead of saying pounds, let's say it's grams. So if you put something on a balance and you had a mass of 1.30 grams, and I asked you to write down your data, you would write down 1.30 grams. This 0 is part of your measurement. Since it is part of your measurement, it is considered a significant digit. And this one would have 3 significant digits. Let's go to this next one. The person that measured with a millimeter ruler is positive of the 9, is positive of the 2, is positive of the 0, but this last digit is an estimated digit. It could go up by 1, it could go down by 1. And again, these are all measurements, and therefore they are all significant. So in this problem, we have 4 significant digits. In the very last problem, again, we are showing with the instrument that we are measuring that we're not stopping at the tenths place, or the hundredths place, or the thousandths. We are actually measuring to the 10,000ths place. So this shows a very precise instrument, and that makes all of the digits in this number significant, which would give us 5 significant digits. Now this is rule number 3 on your cover. Zeros to the right of the last non-zero are significant if there is a decimal point. So let's break that down a little bit more. Zeros to the right of the last non-zero. So this 8 is the last non-zero. These are the zeros that are to the right of that, are significant if there is a decimal point in the number. And there is. So following rule number 3 off your cover is the rule that we would follow in this instance. This next one is one that really gives a lot of students problems. So this is rule number 4. Zeros to the right of the last non-zero number are not significant if there is not a decimal point in the number. Zeros to the right of the last non-zero number are not significant unless there's a decimal point. So if I look at this number would have 2 significant digits. If we were measuring in a lab, this 3 could go up to a 4, could go down to a 2. So we're really saying our measurement is between 2,200 inches and 2,400 inches. These zeros and not having a decimal point there are saying our accuracy really goes to the hundreds place. We go to the next one. This has 2 significant digits. This one is not considered significant. If I put a decimal point there, I would now have 3 significant digits. But with no decimal point, we only have 2. And in our very last example, these 2 are not significant. If I put a decimal point there, it would make them significant. These zeros, though, are trapped, and they are significant. So we have these as being significant digits, so this number has 4 significant digits. Again, if we put a decimal point right here, we would have 6 significant digits. Again, that is rule number 4. All zeros are insignificant after a non-zero number if there is no decimal point. And we're finally to the last one. This particular problem, we call these zeros right here, we call these placeholders. Because what they are doing is they are moving numbers to a certain value, but they have no actual value of their own. So this is rule number 5. All the zeros to the left of the first non-zero are not significant. All the zeros to the left of the first non-zero number are not significant. That is rule number 5. I like to explain this one with scientific notation. I could write this number right here as a 6 times 10, and I have to move the decimal point 1 spot, 2 spots, 3 spots to the third, and since it's less than 1, this is negative third, those zeros disappear. So therefore, they're not significant. So again, this is a 1-digit significant digit number. If I go to the second one, these 4 digits are not significant, so we have 3 significant digits. This one is showing the degree of precision with which we measured. I could write this one as 3.50 times 10, and we have to go 1 place, 2 places, 3 places, 4 places with the decimal point, and it's a number smaller than 1, so we put a negative there. The very last one also can be written with scientific notation. So if I put a decimal point here, I would have 5 digits, but since there's no decimal point, I only have 2 digits. And I could write this as 7.2 times 10, and I would have to move a decimal point from 1, 2, 3, 4 spaces times 10 to the 4th, and those are my only 2 digits that are significant. Okay, now I need to teach you some scientific notation. Many students don't know how to do scientific notation. At least that's what we're finding out in our classes. So there's really 2 steps, 1 and 2. So we're on the back of your 80s right now. It says you move the decimal point such that it is behind the leftmost number, not including zeros. So I'm going to use this example right here. So 0.01230.
Mitch Michalski, please come to the main office.
So my first step is to move the decimal point behind the first non-zero number. 230. My second step says you write times 10, and now you have to look at the power. How many spots did I have to move that decimal point? I had to move it 1 spot, 2 spots, so that's where this 2 comes from. And then finally I look at the number that I started with, this number right here, and it is a number that is smaller than 1, so I put a negative sign there. Stop the video if you need to ponder this for a little bit. Now we're going to move to this number. So 1230.0. Again, that is the first step. The first step says move the decimal point behind the first non-zero number. So it's 1.2300. Put it times 10. How many spots did I have to move that decimal point? 1 spot, 2 spots, 3 spots. And since this number is greater than 1, it is a positive exponent. Again, pause the video. Take a little time to ponder that and look at the examples. Now I need to teach you how to use your calculator. So we're looking for this EE button, and most people that have Texas Instruments, that's right above the number 7. You might have to hit the second button, and then the EE button to get that function to occur. Some students have an EXP button, and some students on some Casios might actually have a 10X button that they have to hit. Come see us if that applies to any of you. But if you type this number in, you would type a 4, a 0.1, a 4, a 4. Then you hit your EE button. You might have to hit the second button to get the EE. And then a 3, and your calculator, after you hit equal, should give you that for a number. This bottom one, to be able to put that one in, you would type a 2, a decimal point, a 2, the EE. Now you have to hit the negative sign, not the subtraction sign, and then a 2, And if you hit equals, you should get this on yours. Sorry, we're out of time.